I will take 5 minutes of your time and remind you a little bit. We are talking about phase transitions. So hello, welcome to the first lecture of the third week. We were talking about phase transitions. Okay. Specifically, the example that we were using last week is of boiling water. Okay. So a kettle, we heat it up, we heat the water. At some point, the water is getting hotter, specifically at the lower plane of the kettle, right? Now, bubbles start to form. What are the bubbles? It's heated up water. So this scenario over here, that water, it actually becomes bubbles of air, of vapor. Okay, we name it a phase transition. There is specific behavior if it's cool enough. For example, over here where the temperature is a little bit lower. Why? Because we heat it up from the bottom up. Right? So the temperature here is lower. The temperature here is much, much higher. Okay? So at some point a phase transition occurs that water becomes vapor. There is a jump in density, okay, or in specific volume of the water, and those bubbles is exactly what we see. All this process of heating up of kettles works only because we have gravity, because what happens? We heat up from bottom, the hot water goes up, okay, the cold water goes down, and this is why we heat the water almost uniformly. In our space, it does not work. We don't have gravity over there. Of course, of course. The density switched from high density to low density. Okay, so you have the same material with much lighter density, so the weight is lower and it goes up. Okay. Now, the mixture of what is the amount of bubbles that we have and what is the amount of water, it depends on the type of the phase transition. Okay. Specifically for water vapor, etc., the sizes of the bubbles, they describe how far away I am phase transition, okay, or at what point with relation to the temperature, critical temperature, I'm constantly are. The sizes of the bubble depends on the temperature of the surrounding area or the surrounding water over here. What happens is that the more we heat up, the more temperature is closer to the critical temperature. Okay? The sizes of the bubbles are going up. Why? Because what we know about phase transitions, of first order phase transition, okay, what we know is that as I cross the temperature, all the surrounding area momentarily, well, at least very, very fast, crosses to the other phase. So I have water near this hot plate, okay? And at some point, if the temperature is high enough, huge portion of all the water inside here is basically transforming into air, okay? This is what we see over here. When the temperature is low enough, I will still have some sort of fluctuations. Small portions, small bubbles will start to arrive, and they will grow in size as I crossing towards the critical point, towards the temperature of phase transition. All right, this is the first order phase transition. We usually describe it with bubbles and water, but it's not always so. So we have a lot of different experiences in our life that are related to the phase transition. The thing to remember is that this is a point when the behavior critically changes from behavior, for example, of A to behavior B. Here, the density jumps. So we have high density water, and then suddenly we have big density. Okay? And clusters of one phase are penetrating into the other phase. What other examples do we have? Very nice example is cornstarch, Ilan בעברית. Okay? So you take this cornstarch, you basically add water, you get this mushy substance. Okay, it's basically mushy. Okay, and it have a very interesting properties. What are the properties? Let's see this video over here. Okay, so we don't have volume. Okay, this is cornstarch, mixture of cornstarch and water. You see he can basically get his hand inside and takes it out. It's not exactly liquid, it's named non-Newtonian liquid. Very great. Sorry? It's like a glue, yeah. But if you apply pressure, big pressure, sudden pressure, you will see what happens. So basically it behaves as a solid. Nothing happens, no splashes whatsoever. So it's not a liquid, okay? You basically can run over this thing, and as long as you apply your pressure hard enough, there is a phase transition. In a normal situation, it's a liquid. But if you apply sudden pressure, you see, you won't sink. Why you won't sink? Because the moment you apply the pressure, and the pressure is high enough, the substance is not a liquid anymore. It's a solid. So that we can continue to run over this thing. It's really fun. I did it myself once. Okay, but if you do not do it fast enough, you will start to sink. Okay, so who is sinking here? I don't know. Okay, he started to sink, you see? The moment you do not apply pressure, it becomes again a liquid and, you know, the different phase. So you can work near this phase transition. Here's another example of the same cornstarch. So they pulled a huge pool out of this stuff. Okay, let's see a guy walking on it. Okay, so he will start walking. Again, as long as he walks, nothing happens. Okay? But the moment he stops, he will start to sink. Again, why? Because he applies pressure all the time. The moment he is simply standing, the pressure is deformating all the local environment, okay? And he will simply start to sink, like this. Okay. Another example, I don't have it here, is sand. Okay. So for example, sand, if you apply pressure, well, if you just take a sand in your hand, it's not a liquid, but you know, you can pressurize it a little bit. But regular sand is very close to a critical phase transition. So if you pressure on it a little bit more, it will become a solid. I haven't included it in this small presentation, but if you, maybe I have it. No, I don't have it. So if you take a bag of sand and apply on it a pressure, it is become instantly a solid. And people use it, for example, as robotic arms. Okay, so you have a robot, and the robot wants to grab this pen. It's actually really, really hard to construct a robotic hand that will manage to grab different objects. So what people use, okay, they will use sandbags. Okay, so you put a sandbag over an object. Okay, the sand is easily deformated. Okay, then you apply pressure, the sand solidifies. All right, it basically obstructs the object. Okay, and then you can lift it up, move it, etc., etc. Another situation when phase transitions occurs, traffic jams, okay, transportation. So you get out of Bar Ilan at 3:30 or 3, okay, there is a still normal traffic on Gea, and you get out of here at 4, and this is what happens, okay. Why is that? It's a phase transition due to number of jumps. So we do not apply pressure, but we can change basically the number of constituents. Okay? So we can define an entropy. We cannot define heat here. We can define entropy. We can define local pressures. And there is indeed phase transitions. Mostly what you're used to are first order phase transitions. Okay? First order phase transitions, all the substance, like for example a bubble, big portion of the liquid becomes vapor. Okay? In the second order phase transitions, there is a huge mixture of both phases. You can consider this like I have a lot of bubbles with different sizes. Okay? So the most classical example we will study, I think in a month from now, is an Ising model for magnetism. So consider each little dot over here is a magnet. Okay? The black one is -1, the white one is +1. So the total magnetism of this block is almost 0, right? Why? Because it's almost homogeneous. There is a lot of pluses, a lot of minuses. They're mixed together, so no magnetism whatsoever comes out of this guy. You lower the temperature, and then you start to see this and that. What happens? So you have self-organization, okay, of, for example, plus magnets together or minuses together. And overall, you will start to see that for different temperatures, the same material will have very different magnetization. Why? Because there are phases of pluses and phases of minuses that are starting to be interlinked with each other. And the cool thing about it, this is actually a second order phase transition, that there is a very interesting fractal properties of the structure of the different phases inside the material. What I mean by fractal properties, well, maybe you've seen the Mandelbrot set, that you zoom in and it still is the same, okay? Or in this nice presentation of Albert Einstein over here, you zoom in, you still get the same phase, you zoom in again, you still get the same phase. It's called scale invariance. The sizes are no matter whatsoever. You can zoom in and you will still get the same picture. And what happens at the second order phase transition is this fractal self scale invariance. We will talk about later in the class. But those are examples of phase transitions that happens all around us, okay? Not just vapor and water. And they are very fascinating and interesting. We'll probably talk about them later. All right. That's enough. Now we will go back to some more boring stuff about thermodynamics of phase transitions. So I remind you, we stopped at a point where we derived the Clausius-Clapeyron. Okay. Wait a second. Okay. So we finished with this equation in mind. dP to dt is S alpha in T and P minus S beta of T and P divided by V alpha and V beta. This is the Clausius-Clapeyron equation, and it determines the coexistence line between the two phases. Right. Now, what we will do next is explore a little bit the coexistence and the properties of those phase transitions. Specifically, we will focus on what happens on phase transitions in the PV plane. Okay. So what I mean by PV, if we plot V as a function of P, okay, we plot it for constant temperature, okay, a phase transition in the PV plane will look like that I have a V dependence on P, and at some point, okay, I will have a jump of delta V, and then an additional behavior of V as a function of P. This is, if I'll plot from experiment the behavior of the volume with the pressure, this behavior over here displays that this jump, a finite jump, displays that I have a phase transition in my system. Right? By the way, how do I know that V is a decreasing function of P? Why won't I write something that is actually a volume, is a growing function of the pressure? Okay. The energy goes up. Oh, it's related to the stability criteria that we derived previously, last lecture. What were the stability criteria? Okay, I will remind you, we had that minus dV for any system and equilibrium is always greater than 0. Specifically, dV to dP is smaller than 0. Those are the stability criteria, okay, for the PV plane. This is why we are using this plane, because we know for any system in equilibrium how volume should behave with pressure. Okay. So what we do expect is to observe some sort of a jump, and this jump will describe to us where the phase transition occurs, how it occurs, etc., etc. So there are two approaches to thermodynamics. One approach is, well, let's measure in an experiment something. Okay, let's measure something in an experiment, and then we'll try to understand what we actually measured. The other approach is a more like of statistical mechanics approach, is let's try and write some models for the behavior, and then we'll explore the properties of the models, and we'll try to understand what exactly happens. So the model we are going to study right now is the van der Waals equation for a gas. Okay. This equation describes a behavior of a gas liquid. It was derived by van der Waals. And his starting point was an ideal gas equation. What is an ideal gas equation? PV, okay, equals nRT. N is the number of moles that I have in my system. T is temperature, R is a gas constant, P is pressure, V is volume. Van der Waals made two corrections to this equation. So this equation assumes, okay, that the gas assumes. They derive it from experiment, right? But the assumptions behind this equation of ideal gas, that the molecules of the gas do not interact with each other, and they basically do not see each other. They only interact through what? Through bombardments of the walls, okay? So they hit the wall, and this is how they create pressure, this is how volume is created. Van der Waals stated the following. So first of all, he said, oh, what volume? Volume is the volume of molecules, total molecules of the plus this free space around them. Okay, so V should go to not just V, but there should be a minimal volume because of the sizes of the molecules. So there should be some quantity B. Okay, V should be bigger than this quantity B over here, or number of moles multiplied by B. Okay. The second correction was, well, pressure. The molecules of the gas attract each other a little bit. This basically should increase the pressure, okay? And his correction was that the pressure is going to be the original pressure plus something that's proportional to 1 over the volume of the system. Okay? So now we have a van der Waals equation, or van der Waals gas. Okay. And this form is that P plus A n squared V squared multiplied by V minus NB equals RT, nRT. Okay. This is our equation over here. Now, for this equation, we can plot the VP or the PV planes, okay, for constant temperatures. Okay, so plot it over here. This is a temperature. Not temperature, I'm sorry. This is volume. This is pressure. Okay. And we have two different behaviors. So first of all, if the temperature is very high, we can plot P as a function of V from this equation. What we will see? We will see that P always decreases as a function of V. Okay. This is exactly what we expect because we know that dV, dP, or dP, dV is smaller than 0. Okay? So the derivative is always negative. This is great. Now, when we start to decrease the temperature, we will start to observe some sort of a shoulder for the P dependence on V. So this is temperature 1. This is T1. We will decrease the temperature. Okay. And we'll start to see that the shoulder is getting bigger. Okay. This is temperature T2. And at some point, what we will start to see that there are actually a minima and a maxima occurs. This is T3. Right? This is a prediction of the van der Waals equation for the gas. Now you will start to say, well, Stas, this is absolutely nonsense because you have proven, somebody have proven, that dP, dV is smaller than 0. Okay? For stability, for equilibrium. What this means is that this region over here, some region over here, is nonsense. Oh, over here actually, right? Why it's nonsense from here to here? Because here the derivative of the pressure with the volume is actually positive. Okay? So this equation does not hold. Okay? And I will say to you, yes, exactly, this is true. What actually happens? What this equation predicts? This equation predicts that there is a non-stable situation, and what physically will happen that the system at this pressure and volume, okay, will jump to some other situation with the same pressure and different volume, okay, and a first order phase transition will occur. So the van der Waals equation, by showing this non-stable behavior, basically saying to us that there is a phase transition in the system. Okay? So the system described by the van der Waals equation, the non-stability, okay, it's not real non-stability. It basically says that this region over here with the positive derivative of the pressure, okay, is a region where where phase transition occur. Now, then we have some sort of a problem. So we have a system that shows phase transition. Okay, think about it in a perspective of the volume. Okay, I can plot down this behavior when I'm plotting volume as a function of the pressure. This is P. This is V. So what we see over here is something like this. Okay? Now clearly, there is something wrong with this part of the function. Okay? There are different volumes for the same pressure. Okay? Different volume for the same pressure. Mathematically is wrong, but physically what it means that this region is bad when described by the function, and what will actually happen is that the system will perform some sort of a jump. Okay? So for the same pressure, we'll observe a jump from here over this point, and there was a jump in delta V, which is greater than 0. Okay. Now, so we have an equation, and you will also study it a little bit more with Michael or David. Okay. Now, what we want to describe is how we can take this equation and correct it for this region to actually show what exactly happens over here, and also maybe from this property of instability, say what exactly, at what pressure and what volume will the phase transition occur. Because the only thing that I'm saying to you that, yes, for this temperature, when this temperature is low enough, okay, and this instability develops over here, there should be some sort of a phase transition between a specific pressure and specific volume to a specific different phase. Okay, we can call it, this is phase alpha over here, and this is phase beta over here. So we have a phase transition from phase alpha to phase beta. At what volumes and at what pressures this phase transition will occur. So in order to answer this question, there is a technique, this technique called Maxvill Construction. So the whole point of the Maxvill Construction is to overcome the non-physical properties of this region over here and say what exactly should happen in this region, or what I think what should happen in this region, and how I find the proper pressure and the proper volume for which the phase transition will occur. Any questions so far? No? All right. Okay, so what is the Maxvill construction? The Maxvill construction uses the Helmholtz free energy. Okay. Remind you, the Helmholtz free energy is the energy minus Ts. The differential of the Helmholtz free energy, dA, it is minus S dt minus P dV plus mu dN. Right? Now, we're looking over here on the behavior for constant temperature. Each line over here is plotted for different temperatures. But over the same line, the temperature is not changing. So if I'm looking over this one specific isotherm, okay, T is constant. Okay? Now, if T is constant, and I want to plot the Helmholtz free energy as a function of the volume, if I plot it, so this is A, this is V, okay? From this equation over here, let's forget about that I don't have a change of the number of the molecules inside my system. I see that dA to dV equals minus P. Okay? So also for the Helmholtz free energy, okay, the behavior of this function with volume should be a decreasing function. A phase transition for me is in the region where there is some sort of an instability will occur. So when the derivative of the free energy is actually not decreasing but increasing. So the region where phase transition occurs, okay, in this region, A will do something like this, okay, by using this formalism of van der Waals equation, okay, since the pressure with the volume goes up, also A with the volume will not going down. All right. Now, we want to find the specific V alpha and V beta where we are saying there is a phase transition. Okay? There are going to be A alpha, okay, the value of the Helmholtz free energy with phase alpha where the phase transition occurs. At this point, the volume of the system is going to be the volume in phase alpha, and the system, we expect it to jump, okay, to a different volume, okay, where the phase is already phase beta. So here it's alpha, here the phase is beta, and here the volume is V beta. The value of the free energy at this point is A beta. Okay? We don't know what is V alpha, what is V beta, what is A alpha, and what is A beta. We only know that there is some region over here where a phase transition occurs, and we know that there's supposed to be a jump from V alpha to V beta. Okay, what do we know? That at the phase transition, the pressure is the same for both phases, and also the chemical potential, and also the temperature. Why do we know it? We obtain it from the stability criteria that we developed before. If we take those two phases together, there is an equilibrium, and the criteria for this equilibrium is the equivalence of the chemical potential, the pressures, okay, and the temperatures. The temperature is exactly the same because we are looking on an isotherm. Okay, so we want to use the constant pressure criteria and, more specifically, the constant chemical potential criteria. What I mean by that, so we know that at this point the chemical potential is mu alpha. We also know that at this point the chemical potential is mu beta. And we know that mu alpha equals mu beta. Okay? Because this is exactly at the critical temperature. So what we know and what we want to use is that mu alpha equals mu beta. The chemical potential for phase alpha equals the chemical potential for phase beta. How we are going to apply it to the Helmholtz free energy, we're going to use this equation over here. So what we have in this equation, first of all, let's get rid of dt. The t is constant. Okay? So dA equals minus p dv. Mu is also constant, right, from one phase to another, plus d mu n. Okay? From this equation, what we obtain that dA plus pv equals to d mu n. Or more specifically, A divided by n plus p v divided by n equals mu. So from here, and the knowledge that we have mu alpha equals to mu beta, we obtain that A alpha divided by n plus p v alpha divided by n equals to A beta divided by n plus v beta divided by n multiplied by the same pressure P, because the pressure is also the same for the two phases. Okay, instead of saying A divided by n and V divided by n, we will write A alpha is A divided by n. Okay, this is a free energy per mole of molecules, and V divided by n, we'll use something like me over here. Okay, so our equation over here is A alpha plus P me alpha equals A beta plus P me beta. Okay, and from this equation we obtain that A alpha minus A beta equals minus me alpha minus me beta multiplied by P. Okay? And finally, we obtain that A alpha minus A beta divided by me alpha minus me beta equals to minus P. Any questions? Yep.
Why did you say that dA is minus PdV plus mu n?
This equation over here. Yep. But I said that mu is constant when going from one phase to another.
N is also constant.
I don't care. Okay, let's assume that it's not constant. I don't care. The only thing that I care that is mu is constant, and then I can divide by n. See, this guy over here, when mu is constant, I can say that this is d mu n.
So n is
Well, it can actually change, but what happens is n at each phase changes. It can go from one phase to another. The total n is constant. Yes.
so dn is not zero.
Well, we start with the situation that it's not zero. Yes. Yes, this is how we derive this equation over here. So if we neglect dn in this equation, we won't have any dependence of the free energy on the chemical potential. So we must not assume that dn is zero. Right? Further questions? Okay. So we have this equation over here. What it means? Let's go back to this plot over here. We don't know what A alpha is. We don't know what A beta is. We don't know what B alpha is, and we definitely don't know what mi beta is. We don't know all of these guys over here. The only thing we know, okay, the only thing we know is that this quantity over here actually equals to minus P. Okay? What do we know? We know that dA to dV equals to minus P. So the derivative of A at this point is what? Minus P. The derivative of A at this point is also minus P. Okay? Now, what this guy over here says. This says that we should take A alpha, we should take A beta, we should divide it by V alpha and V beta. So basically we should connect those 2 points by a straight line. Okay? The slope of this straight line is minus P. Okay? And this slope is exactly the slope of a tangent line to the function to A at this point, and is exactly the slope of a tangent line to this function at this point. Okay? So we build up a continuity of this free energy, which basically we're saying we will find points such that the derivatives of both those 2 points are exactly the same. Okay? And we will connect those 2 points by a straight line. Yes?
Those 2 points are the 2 points that are on the left vertical line?
Where? Over there? I don't know. I don't know. Okay, I'm saying there should be some transition at some specific volume. they're not exactly the same. I want to define them. I want to find exactly when the transition happens. Okay? I don't know at which volumes or at which pressures. This construction here, due to Maxvill, helps me out. Why? Because in the middle, it's not a physical description. I'm trying to find a physical description for those intermediate values, but the only thing that I can say, I know that the system will jump from here to here. What are the volumes where it will jump? Let's construct this thing over here, and we will find out. Okay? Yep. Yes, yes, yes. Otherwise they are different, because mu is going to change. Only in the vicinity of this phase transition the chemical potential is not changing. It's not varying. Okay. So I found, or Maxvill found, a way to construct, okay, a continuity for the free energy, right? And by doing so, actually define what are the critical volumes and what are the critical pressures. How so? Because I can now go to the PV line, right? So what happens on the PV plane? I have this P and V, right? This is my construction over here, okay? And let's use this definition over here in order to find a criteria how to find the critical volumes, not for using the free energy, but actually using something which is related to the pressure and volume. Those are much more plottable quantities. It's hard to imagine what this free energy is. Okay? So what exactly I'm going to do? I'm saying the following. Look on this equation over here. This equation states that A alpha minus A beta equals minus P multiplied by V alpha or ni alpha, ni beta. Doesn't matter. Okay? What it says, that I have V alpha over here. I have V beta over here. Okay? I have some pressure that I don't really know what it is. Okay? I have some pressure. This guy on the right hand side says this pressure, let's call it P, multiplied, so the height of this rectangle multiplied by the base of this rectangle, okay, minus is the difference of the free energy. So what is calculated over here on the right hand side without the minus is this area beneath this value P. Okay. Okay. But I also know that dA dV equals to minus P. So if dA dV equals to minus P, okay, then A alpha minus A beta equals to minus integral from V alpha to V beta P dV. Now there should be an equivalence of those two guys, right? So what I'm actually looking for, I'm actually looking for P and V alpha and V beta such that P V alpha minus V beta equals to an integral from V alpha to V beta P dV. So P here, let's call it P constant, PC. This is our PC over here. What the equation means that in order to define for what volumes and for what pressure the phase transition will occur, okay, I must find a pressure such that the area of this rectangle over here will be equal to let's use this. Will be equal to the area beneath this. Oh, this is not that. This function over here. Okay? So this is equivalences of the two areas. The area of the rectangle and the area between the function, between the values V alpha and V beta and the V axis. Right? So I need to find such V alpha and V beta, okay, and such PC, such that the left-hand side will be equal to the right-hand side. How I know how P behaves? I know because I have this equation of state given me by the van der Waals, right? So P plus A n squared divided by V squared multiplied by V minus B equals n RT. Okay? I can find the P dependence on V, okay, put it inside this integral, perform the integration, okay, and then I will find the PC. Okay, this is how I find, if I know the equation of state, if I know how if I know how the gas, the pressure depends on the volume, I can, by using this Maxvill construction, in order to actually construct and find the specific values for the pressure and specific values for the volume in order to solve where the phase transition occurs. Yep.
What is physics meaning of this state? It says when the phase transition occurs, the pressure of the system.
Yep. Exactly. But it's an approximate. It's according to Maxvill construction. You can show that this is very, very close, okay, to the actual value, okay, of the pressure. But you never know. How you can find out? You have to measure, right? Here you see that there is a non-stable situation in the van der Waals gas. How you define where exactly the phase transition occurs, at what pressure. This is one way to define it. Okay? And P and V, so P and V alpha is the pressure and the volume in phase alpha when the phase transition will occur. And P and V beta is the pressure and the volume when the phase transition will occur for the beta phase. Right? Yes? Well, I must find it in, first of all, you will see it, okay, not here, but in the exercises. But you find the P, the only thing that matters that the errors are be equivalent. This is enough. That's basically enough. Well, the only thing that you can know for sure is, first of all, look. V alpha, okay, you can basically say what is V alpha. V alpha is dictated by P. Okay, you can find what is V as a function of P. The same goes from V beta. So you have only an equation of P's over here, eventually. Okay? You just substitute the behavior of V with P inside this equation. Any other questions?
As the phase transition,
yes.
So there's P, but why this unstable process occurs?
Okay, because this is a model. So van der Waals or any other physicist, chemist, whatever, we think of how the system should behave. The meaning of I will write a homogeneous equation or some sort of equation, okay, that will describe the system is simply wrong. Why? Because there is an underlying assumption beneath the fact that I write that the equation of state of the gas is P plus something, V minus something equals something. Here I assume when I write this down that everything is homogeneous, right? Everything is absolutely homogeneous. I have phase A, which is homogeneous. Maybe I have phase B, but the media is a homogeneous media. What happens in reality? We've seen that those are bubbles of two phases that are mixed with each other. Everything is unhomogeneous. Nothing is homogeneous inside in the system when you're very close to phase transition. So there is no way to write any normal equation that will define to you something. This is why your equations start to show some sort of instabilities, etc., etc. Right? This basically means that all the purpose of writing down an equation for the phase transition, assuming that everything is homogeneous, is simply wrong. This is what it means. Okay? And this is why we see all those instabilities and A goes up with volume. It's simply unphysical situation when you assume that you have a phase transition and a homogeneous behavior of your system. It's not like that. There are bubbles. Okay? And then you cannot write this down.
So the experimental result is just a straight line?
The jump. You will see a jump.
Oh.
Okay? You won't see anything here. There is no situation when you have, okay, V alpha plus V beta divided by 2. No such thing, because your material cannot be at this volume. It can be either in this phase then its volume is below V alpha, or it can be in this phase, and then its volume is above V beta. Anything in between does not exist. Okay? You cannot describe the material with the volume that looks like this in between. The equation will try to say, yes, yes, there exists a state that looks like this, but it's wrong, simply wrong. Okay. Maybe another way to describe it is if we plot for each temperature, okay, let's look like this. So if we're plotting this P against V, and we're plotting an isotherm, okay? Plotting this isotherm. And let's assume for this isotherm, I found the two precise for each T, okay? I found V alpha and I found V beta. Okay? I used this Maxvill construction, I found V alpha and V beta. Then, for each temperature, because I can have a different isotherm, I can have this one. And for this one, there are going to be different V alpha and different V beta, because here is T1, here is T2. There are difference in temperatures. Then there is difference in pressures, critical pressures, and critical volumes. So for each temperature, I will plot V alpha, okay, when the lower volume and the higher volume. Okay? And I will do it for many, many, many temperatures. What I will start to see, okay, there is a jump in volumes, right? I'm at a specific temperature. I can have all the volumes up to here. I cannot have any volumes between V alpha and V beta. And then I have all the volumes above V alpha. Now, if we plot all the different transitions volumes for different temperatures, we will start to see a plot like this. Okay? So here is phase alpha. Here is phase beta. Okay? Here is unstable situation. There are no volumes at specific temperatures, okay, that the system is all homogeneous something, media, with a given volume and a given pressure and a given temperature. It does not exist, because it's a mixture, right? And the interesting thing is that there is only one single point that's a maxima of this structure that I built over here. When the single point occurs, okay, so for this PV, it will be exactly at a temperature, then I do not have a minima and a maxima, but those two minima and a maxima will collide in one single point. Okay? Something like this. This point I call, or not I, this is the critical point. What happens at this critical point? What you see, it's at a given temperature, there is only one single volume. Okay? Only one single volume. So there is a phase transition exactly at this point, but there is no jump in the volume between phase alpha and phase beta, between the liquid and the vapor. There is no jump, okay, in the volume. Of which order this critical point is? This is a second order phase transition. Okay? First order phase transition, there are jumps, there are discontinuities. Second order phase transitions, okay, they are named continuous phase transitions, and we'll see that there is no jump in the volume. Okay? Anything be above that, there is no phase transitions whatsoever. But specifically at this very peculiar point, another phase transition will occur, because on this side I will have liquid, on this side I will have vapor. Okay? And a lot of interesting physics happens in the vicinity of this point, critical point over here. The fractal properties that I mentioned, the huge mixture, that everything is actually mixed together. There is no separation of phase alpha and phase beta. Everything is mixed together on all the different length scales of the system. So this is a point named critical point, or point of second order phase transition. Okay, so we're finished with this. Any questions? No? Yes? Great. Going forward. So this part, we're leaving thermodynamics behind, and we're starting statistical mechanics. So if you look behind of what we have done so far with all this thermodynamics for phase transitions or not phase transitions, we have those assumptions that everything is homogeneous. We have continuity equations. We don't care about what happens inside. We don't care what are the different interactions. We even don't know that there are molecules. We have a continuity equation for the matter. Statistical mechanics is different. Statistical mechanics, it tries to go from bottom to up. It starts with a model. It starts with a description of the system, simple description of the system, and it tries to build up an apparatus to deal with this humongous number of particles that are in every physical system. Okay? So the approach is very, very, very different than from what you have seen so far. Now, but this is a problem, because if in thermodynamics I had not a clue about what's going on inside, I have those continuity equations. Here I have to start with 10 to the number 20 10 to the power 23 molecules, particles, whatever. Okay? Now we know that our world is a quantum world. So in order to describe what happens in the system, I have to solve, okay, I h bar d to the t psi equals to Hamiltonian that is operating on some psi over here. And it's an enormous Hamiltonian, and it's an enormous Schrödinger equation that describes how the system evolves, and I need the knowledge in order to solve it of all the different particles inside, and I'm basically lost. Okay? Completely lost. One can say, well, forget about the statistical mechanic approach, let's go back to thermodynamics. But we actually have a hope. What hope it is? We know from thermodynamics that there are very few parameters that describe equilibrium states. Okay? For equilibrium states, in order to describe it, what we used? We used pressure, we used volume, maybe even not, chemical potential. Very few parameters in order to describe what an equilibrium state is. Okay? Now, our hope is that maybe the same few numbers of parameters will also somehow we can obtain from the quantum mechanical or classical description. Okay? And the point from starting out from this description is to say, well, in quantum mechanics there are distinct states of the system. Right? So the system at each specific point, there are it can be a discrete set of sets or a continuous set of sets, but there are states of the system that it can occupy, okay? And we can describe the different properties of the system if we know at which state the system is currently occupying, or how it transits from state A to state B and then to state C, if we will follow it as a function of time. Maybe we will also gain some sort of understanding of how the system changes its states. So the states are at least clear in quantum mechanical. So what I want to do eventually, or not me, the statistical mechanics approach, is to follow the system as it changes from one state to another. Okay? Now, in quantum mechanics, it's simple because there are states. What happens in classical mechanics? There are no states in classical mechanics, right? Well, actually there are, okay? Or at least I can define them. So in classical mechanics, in order to define a state of a system, you learned it from analytical mechanics, I need to define the phase space, right? If I have n molecules, so I will define all the positions of the different molecules, okay, Rn. And I will describe all the momenta, or generalized momenta, of all the different molecules in my system, P1 till Pn. Now, then I can describe the system as going from one point in this 2n-dimensional phase space to another, and say, well, the system changed its state from one point to another. Okay? For example, a harmonic oscillator. Okay? If we plot p as a function of x, okay, looks like this. So there are specific closed lines. Okay? And the system, how it evolves with time, okay, you put a point on this line that is dictated by a solution of in the phase space, and Newton equation or Lagrangian equation, whatever, but generally F equals ma, they dictate how this point, okay, will flow from one position in this phase space to another position in the phase space. Okay? So usually, for example, it will grow in this way. So we can look on this point, which is, for example, an oscillator, a pendulum, right? And we'll follow its motion in the phase space. So all the different states, I will say, are different small portions in my phase space. Okay? So it's much more easier to say, well, I have a state in quantum mechanical form because it's natural due to the properties of the Schrödinger equation. But the same thing, the same approach I can invent for classical system. I can say small portions of my phase space are the states of the system. The pendulum was at position x with velocity p divided by m, and after a while it moved to a position x2 with velocity p2 divided by m, right? And then I can follow it and describe the evolution of the system as it jumps from one state to another state, to the third state. Okay? In general, okay, in classical physics or in quantum physics, the only thing that matters for me is that I assume that there are states, okay? Let's picturize them as those squares over here. They can describe the energy of the system. They can describe the relation of the momenta to the position of the system. Okay? And each square is a state where the system is located. Okay? And what happens as I trace my system as a function of time, it spent some time in this area, in this region. Then it jumped into this region, spent some time over here. Then after a while, it spent into this portion of the phase space, and then it jumped over here and spent some time over here. Okay? What I do in experiment, okay? In experiment, I follow the system. For example, if I measure the kinetic energy, okay, I will measure it as a function of time, right? If this is time, this is my kinetic energy, 1/2 mv squared, and I have noise inside my system. Okay. How it will look like? It's some noisy function, because I have temperature. Right? It won't always be a constant energy. It depends on what is the dynamics of the system, how it jumps from one place to another, etc. And I follow it as it changes from one state to another, to the third, etc., etc., etc. Why it's important? Because all those fluctuations, different fluctuations, I really don't care about them. Sometimes they're large, sometimes they are small. In order to describe something statistically without taking into account all the different molecules, I will have to use averages. Okay? And averages for me is, well, this is the average kinetic energy. All the different fluctuations over here, okay, depends on the system, depends on the temperature. I don't really care about them. Okay? So what actually I do in order to find the average in experiment, okay? In experiment, I do the following. I say the average energy for the system that I followed, okay, is, let's assume that I performed n measurements during time t. I measured the position of the particle of this system here, and here, and here, and here, etc., etc. So what is the average energy? It's the sum of all the different times the energy that I measured. I goes from 1 to n, okay, and I divide it by the total number of measurements. Okay. So this is what an experimentalist will perform. I will ask him what is the energy of the system. He won't measure it once and say, well, the system is, this is the energy. He will plot a graph like this, okay, and will take an average. How he will make an average, or she? By using this function over here. Right. So this is an experimentalist perspective. It's great if you're an experimentalist, and if you're a theoretician or experimentalist that don't want to actually perform all those measurements but want actually to calculate something, you need some other tool, because you cannot all day long follow your systems, right? You need to do something different. Well, the other different thing that you can say is the following. Let's, instead of summing of all the different energies that I've actually occupied during time t, okay, let's sum up over all the different possible energies that are in the system. Okay? I will sum up over all the different states in my system. This is the state perspective. I have a state, and I visited different states as a function of time. Instead of I'm saying I will calculate this quantity when I'm summing up over all states. So how I do it, it's the same energy. I do it in the following fashion. So let's sum up. Me is a sum over all states of the system. Okay. E is the value of the energy per each state, per state. Okay? At state 1, it was E1. At state 2, it was E2. Beforehand, I counted on the different observables. Now I'm counting on all the different values, possible values. Okay? And inside, I will have 1 over n, the number of times system, or the system, visited state me. Okay? All right? And all of this multiplied by ini. Okay? So those two averages are equivalent. Right? If I haven't measured or haven't seen E23, it won't be part of my averaging procedure over here. Okay? So what I'm doing here is I'm counting the number of times I visited a specific energy. I divide it by the total measurement times, and I multiply it by the value of the energy of each state. Beforehand, I sum up all the energies that I've seen. Here I'm summing up over all the energies that I know that there are inside all the different states, and I multiply it by the number of times, okay? I multiply it by the number of times that I actually visited this precise state. Okay? Then we can do the following thing. What is 1 over n? And here the number of states the system, or the number of times, it's not of times, the system visited state nu. Okay. What is this? So let's assume that I'm doing this experiment for extremely long times. Very, very, very long times. Okay? The number of states that I visited, the number of times that I visited state ni, divided by the total number of observations, I call it P ni. There is some sort of an assumption over here. What is P ni? The probability to observe, okay, state ni. Okay. So this assumption over here, or statement over here, states that if I follow the system and I count the number of times that I visited state ni, I will divide it by the total number of my measurements. Okay. This ratio over here is the probability to observe, okay, state ni. Now, this probability to observe state ni, I can say, well, it's no longer a time-dependent quantity. I can say that this is a static quantity which depends on the ensemble of the systems. Or what I will do, okay, I will calculate different properties for the energy, not by following one single system, okay, that it will be for a specific amount of time at state 1, for a specific amount of time at state 2, for a specific amount of time at state 3, etc., etc., etc. I will do the following thing. Instead of following one single system, I will say I have ensemble of different systems, or the same systems. Okay? And I will say that now I will take this system, and it's in state 1. I will take another system, it's in state 2. I will take another system, it's in state 3, and I measure the average quantities, okay? I will measure the average quantity not by following all the different systems, but by saying, okay, the average E, let's say it's called ensemble averaging and not temporal averaging, is what? I define it like this. The probability to pick up from all this ensemble of different systems, this system with energy in E. Okay? This is ensemble averaging. I don't care how the system evolves. I say I pick up a system with probability P ni, and the value of the energy for this system is E ni. It's not moving in time, nothing really happens. It's termed ensemble averaging. And the basic property of statistical mechanics is that this guy over here, which is time averaging, okay, the basic assumption of statistical physics, it's called the ergodicity assumption. Ergodicity assumption is that time average equals ensemble average. So instead of following a system, I will take a system, I will calculate the probabilities to observe or to obtain system with energy E1, the probability to observe a system with energy E2, and I will count them all together in a static fashion, without time dependence, without nothing. And the basic assumption, it's not a theorem, it's an assumption, because for some systems it does not work. Okay? It's called an ergodicity assumption. Okay? It means that I can work without time dependence, I can work in my lab, okay, calculate different stuff, and then go and say your averaging procedure for your real system is A. Why is that? Because of this assumption over here. And surprisingly enough, it works. Okay? It works for a huge number of systems. Sometimes it breaks. When it breaks, for phase transitions. For phase transitions, this ergodicity sometimes does not hold. We will see why. But what we will do right now, instead of trying to assume that everything is homogeneous, right? We will start by describing what ensembles of systems we can use, okay? What models of systems we can use, for which we can somehow calculate not only the different energies, but also the different probabilities of occurrences of a specific part of this ensemble. Okay. Now this is when specific models become important. Because I cannot solve this Schrödinger equation or a general Newton set of equations for any system. But what I can learn a little bit is how those procedures of ensemble averaging occurs for models that are simple enough. And surprisingly, this teaches me a lot of also about some very complicated models. Okay? So what we will do now, in this lecture and the next lecture, is actually to define what ensemble of systems I can use and how I can calculate this averaging function that I wrote down here. Any questions? No questions. So I have to invent ensembles, okay? And I want to invent ensembles that are simple enough such that I can perform this averaging procedure over here. So the first ensemble that I will have is termed microcanonical ensemble. Okay. What is a microcanonical ensemble? I don't know what the model I will use yet. I don't care about the models, but there should be some statistical properties that any model should satisfy. In the microcanonical ensemble, there are several assumptions. Okay? What are the different assumptions? First of all, for any system, okay, that is described by this part of this microcanonical ensemble, all the different representations, all the energies of all the different states are exactly the same. Okay? All the states have exactly the same energy. Okay? I can also assume well, then it's a little bit of a problem. Why? Let's think about it from a quantum mechanical perspective. They have a system, okay, and this system in a very specific state A, okay, with energy E. Okay? Why, if it's a coherent state, it should jump from state A to state B if the energy of state B is exactly the same as the energy of state A. It won't happen, okay, from the quantum mechanical perspective. Now, we're assuming that there are always some small noise or some vacuum fluctuations that force the system to perform this jump. Okay? So the system actually, as a function of time, samples all the different states. Right? All those different states have exactly the same energy. We also assume another thing. Right? Remember, here I must tell you something about what are the probabilities to find a system in a given state. For microcanonical ensemble, it's very simple. All the probabilities of all the different states are exactly the same. All the probabilities P mu are exactly the same. The energies of two states is the same, so the probability, at least at this ensemble, this set of different systems, so the different probabilities, they're not different. They're exactly the same. Okay? Those are the two assumptions of the microcanonical ensemble. Right? They are very important. Okay. Now, eventually, we want to calculate something like this, the average energy. So the average energy we can calculate by assuming that all the different states are the same and all the different energies are the same. Nothing really happens, for example, for this quantity over here. Why? Because here we assumed, okay, that the energies are exactly the same energies. But there are some other interesting properties like the entropy, okay, that we can calculate for the microcanonical ensemble, okay, that might give us some clue about what happens to the system. So I need a procedure that will connect those statements of microcanonical ensemble, so equivalence of or the same energy and the same probabilities, to some physical quantities. What are physical quantities? Pressure, volume, temperature. Forget about pressure and volume. Temperature. Okay? I want to connect those statistical statements to temperature that I can go and measure, or at least understand a little bit what's going on. Right? Now, there are relations between temperature and entropy. Okay? We know that they are related somehow because they are related due to heat for thermodynamics. Here I don't know what heat is, what temperature is, I don't know absolutely nothing. The only thing I said that I have different states and I have the same energy and the same probabilities. But I can look on the situation and say, well, there is a very nice thing about entropy. The nice thing about entropy that we found out that in equilibrium it has a maximal value. And if I apply a constraint on the system, what happens to the entropy? It goes down. It lowers. Okay? Great. So I want to find a property that's related to those concepts over here that behaves in the same way as the entropy behaves. Now here I can say, what is going down if I apply internal constraints on the system? And the answer is the number of states of the system. Okay? The number of different states of the system will decrease if I am saying, well, I'm only interested in the states that are satisfying such and such constraint. Okay? So application of any constraint for this microcanonical ensemble decreases the total number of states in my ensemble, because suddenly not all the states satisfy this constraint anymore. Okay? So I'm making an additional state. I'm saying, well, let's make entropy and the number of states of any given system be equal to each other. Okay? So entropy is the number of states. There is only one minor problem. And what is the problem? That entropy is extensive property. What is the number of states? Is it extensive? Intensive? What is it? Great. So let's look on an example. We have a single dice, okay? And the different states of this dice, we roll the dice, and it can give us one number. 1, 2, 3, 4, 5, 6. So the system for us, this is our system. We roll the dice, okay? We get an answer. All the different answers are equivalent. They have exactly the same probability. They have, I don't know what's the energy here, but it's exactly the same energy. Right? The number of states of a system of a single dice, okay? It's 6 states. If I have 2 dice and I roll them together, how many different states I will have now? 36, okay? 36 states. So the number of states of a system, okay, is not extensive, but it grows up in a multiplicative manner, right? If I'll have 3 dices over here, is 6 to the power 3, etc., etc., etc. So entropy and the number of states cannot be equal to each other. But there is a solution. What solution? Log function. Okay? If I'll take log of the number of states, it will become an extensive function. So the next assumption of my microcanonical ensemble is that I will define entropy as the logarithm, normal logarithm, of the number of states. So omega number of states of the system. Okay. The entropy is K Boltzmann log of omega. The value of this K Boltzmann is, you never remember it, K Boltzmann equals to 1.38 multiplied by 10 to the minus 3 Joule per Kelvin. Why I need this constant? This is a number, a log of a number is a number. This have some sort of entropy. Entropy, what are the values of entropy? We know that 1 over T is ds to dE, okay? So it has to have some Joule over Kelvin units, right? This is why we introduced there a specific constant called the Boltzmann constant, which will agree to a specific scale, okay? So we reach this point that we know for a given system, okay, we know how to calculate different physical quantity. Entropy is already a physical quantity. It can be related to temperature, it can be related to energy. Okay, if we will calculate the number of states of a system for a given energy, okay, let's assume that we will obtain omega as a function of E, okay, we can calculate this derivative over here and relate our entropy to temperature. It's going to be a measurable quantity. We can discuss it, we can understand it a little bit more, we can relate it to the thermodynamics that we already know, okay. So this is what the plan of attack for this microcanonical ensemble. We're going to use simple systems, simple models, okay. We're going to use those assumptions because first state we will assume that we have microcanonical ensemble, okay. We are going to calculate the different number of states because the moment we know what is the different number of states, we know what the probability to be in a given state, what it is. 1 over omega is the probability to be in a very specific state of the system. The moment we know the number of states, we can calculate the entropy, and the moment we know entropy, we know everything else, what's related to the system. We won't do it today because it's a tedious task, but this is what we are going to do on Tuesday. Thank you.